Hello, welcome to the fifth video in the series, and we'll be discussing nuclear chem and molecular orbital theory. First, we're going to talk about nuclear chemistry, which is mainly concerned with the nucleus, and so the atomic numbers, or the number of protons in the bottom left-hand corner, as well as the mass number, which is the number of protons, plus the number of neutrons in the upper left-hand corner. So I'm just going to quickly go over some of the notation. So a proton is designated with a P with a 1 and 1, neutron with an N and 1 and 0, electron with an E and 0 and -1, and a positron, which is the antiparticle of the electron, is designated with a 0 and a +1. And here is an example of the types of reactions that are involved. So going from a neutron to a proton and electron is an example of nuclear decay. And there's also the reverse with a proton and electron going to a neutron. And a third example is an electron and a positron making gamma radiation. And for example, this occurs in PET scans. Another example of a particle is the alpha particle, which is a helium atom with 2 neutrons, and so it's designated with 4 and 2 respectively, but you most commonly see it with the alpha symbol rather than helium. Next, we're going to discuss the band of stability, which is, as the name suggests, where the elements are most stable. And so it starts off at an almost 1-to-1 ratio between the number of neutrons and the number of protons, but then it gradually becomes more stable with greater neutrons than protons. And so this band has different degrees of stability. So at the core it's the most stable, and then it goes out to relatively stable. But as you move further out from this band, there is less stability until then it ceases to exist. And as a fun fact, lead is the largest atom that's stable. So next, I'm just going to talk about different types of decays that we can use to get back to the band of stability, and so that's positron alpha and beta decay. So starting with alpha decay, it gets rid of 2 protons and 2 neutrons at the same time. So it's generally used if you want to move down into the line. And next is electron capture, and this is for losing protons while gaining neutrons. And so this is particularly helpful if it is below the band of stability, and so it would be moving to the left and up. And so this uses that proton plus electron goes to neutron. And this is actually the same thing as positron decay, which is a proton goes to a neutron and a positron, and decay means coming out while capture means gain, which is why for positron decay the positron is on the product side, while for electron capture the electron's on the left side, but both do the same thing. And finally, the last type is beta decay, and this is for losing neutrons but gaining protons. And so this is for when it's positioned above the band of stability, and so this decay causes it to go down and to the right. So this uses the reaction, the neutron goes to proton plus electron. And for each of these, as with the band of stability, protons are on the x-axis and the number of neutrons is on the y-axis. So an interesting application of this is fission, where we break up and cause the nuclei to release large amounts of energy. So a neutron is bombarded into a nucleus, which breaks up into daughter nucleoids and releases neutrons and energy. And so this is a reaction that grows exponentially with a 1-to-3 ratio. Our next topic is transmutation, where you hit a nucleus with something, it takes it in, and it destabilizes the nucleus, and so we've got a particle coming out. And so this is the general format of what you may see, where there's an element, and what's in parentheses is what goes in, comma, and what goes out, and then we have the final, what's left over. One example is if we have B with 10 for the mass number and an alpha particle and a neutron, and then a nitrogen with 13 for a mass number. So what's happening here is that we're hitting boron 10 with an alpha particle, which destabilizes the nucleus. So a neutron comes out, and we're left with nitrogen 13. So we can also rewrite this out as a reaction. So we know that boron is 5 and nitrogen is 7, which allows us to rewrite it like this. And here's another example. If iodine 131 goes through beta decay, it could also be written as I-131 goes to E plus something, which we can then determine based on the mass number and atomic number, which must remain the same on both sides. So if we have 131 on the left side, then there must be 131 on the right side, since E has the mass number of 0. And then for the lower number, for an electron is -1, so that means that the atomic number of this element must be 54, which makes it xenon. And here's a final example. We're asked to illustrate the positron decay of nitrogen 13, and so we can rewrite this as nitrogen, which has an atomic number of 7, 13, goes to that positron with a +1 on the bottom left and a 0 in the upper left, plus we know that the mass number must be 13 since an electron has a mass number of 0, and the atomic number must be 1 less than 7, making it 6, which means it must be carbon. And for electron capture, we get the same answer as this, except the reaction would just look a little bit differently with the electron on the left side rather than the positron on the right. And lastly, this is a radioactive process, so these are all first order reactions. So they're not chemical reactions, but they do follow the first order reaction. And so they use the integrated rate law for first order, which is ln of the concentration of A, although this can also apply to mass or pressure or anything proportional to concentration. And that's equal to -kT plus ln of the initial A. And then the half-life equation was ln 2 over K. And the last topic is molecular orbital theory, and so it involves bonding and antibonding. So it says that if there's an electron in the s orbital, and we call it A, and we add that to an electron in the s orbital, we call that B, that would be positive and positive phases, and so that leads to bonding. But if it were subtraction instead, so the A minus B, it would be positive and negative, which is antibonding. And so in general, if something has strength, it's low potential, and so electrons lose potential to be in bonding. Let's jump right into an example. So we're going to be doing H2, and we're going to order this in increasing energy as we go upward. So we can label HA and HB, they each have 1 electron, and we have 2 options where they could be either bonding, which is sigma 1s, or antibonding, which is sigma 1s star. We know that higher potential energy is less stable, and so both electrons will be in the sigma 1s bonding. And as always, they have opposite spin. And as a reiteration, the low potential energy means more stability. Next up, we're going to discuss the bond order, which basically tells us the strength. And so that's equal to the number of bond electrons minus the number of anti-bonding electrons divided by 2. And so in this case, with diatomic hydrogen, that would be 2 minus 0 over 2, which is equal to 1, so 1 single bond. Next, we can discuss H2 minus. So it's a similar setup here, but one atom has 2 electrons rather than 1. And the priority is low potential, and so first the sigma 1s bonding is filled, and then there's one left over, and so that electron must go to anti-bonding. And so when it comes to bond order, it's equal to 2 minus 1 over 2, and that comes out to be 0.5. And so H2 minus exists because the bond order is greater than 0, but it's not stable, especially when compared to H2, which has a larger bond order, which is better. And this was all just for s orbitals, so next we're going to discuss the p orbitals. So an example of this is B2. And so it has p orbitals that can overlap in 3 different ways: x, y, and z directional. So for x, for example, 2px plus 2px leads to an anti-bonding system for sigma 2p star. And so this resists overlap, so there's no bonding, and it pulls electrons to the opposite sides. But for 2px minus 2px, it's bonding, and so this is sigma 2p. Then for y, 2py minus 2py is anti-bonding, and so that's pi 2p star, since the electrons are pulled out from the bonding area. Then 2py plus 2py is bonding, and so that's called pi 2p. And the z directional is also like the y directional, but just different areas of overlap, which doesn't occur in the nucleus. And there's actually a special rule for p orbitals. So for B, C, N, and those columns, the level actually drops. So pi starts lower than sigma, and it's lower in potential as it's getting filled, but once pi is filled, they have higher potential energy. And so here's how it would be drawn out. And so from top to bottom, it would be sigma star, pi star, sigma, and pi at the bottom. But for O and F, it would be the normal assumed setup, and so it would be sigma star, then pi star, and pi star, followed by pi, and then sigma at the bottom. So if it's homonuclear diatomic, and so it's 2 atoms that are of the same type, it's simple. But if it's heteronuclear, like NO or CO, we still use the same type of trend, but it's almost as if we take the average. And going back to our examples, let's go ahead and do B2. So once again, we go from low energy at the bottom to high energy at the top. And we can start by drawing the s orbital. So we have 2 atoms of boron, and so they each have 2 electrons. And this makes it so that both sigma 2s and sigma 2s star are filled with 2 electrons each. And next we can draw the p orbital. So both atoms of boron have 1 electron. Then we use the same trend as before, so going from low energy to high energy, that would be pi 2p and pi 2p, and followed by sigma 2p and pi 2p star, and sigma 2p star. So that makes us put 1 electron each in the pi 2p, and overall this makes it paramagnetic. And so this is why it's attracted to magnetic fields. And the bond order for this would be 4 minus 2 over 2, which is equal to 1. And our final example will be a heteronuclear molecule. So we'll do carbon monoxide. So we know that carbon has an electron configuration of 2s2, 2p2, and oxygen has an electron configuration of 2s2, 2p4. Then if we write out B, C, N, O, F, C, and O, if we take the quote-unquote average of it, it falls at N, and so we need to follow the left pattern. And so we can draw out the p orbital so that 2p2 is on the bottom, and going up that would be sigma 2p, then pi 2p star, and then sigma 2p star. And now we can do the same for S, and so it'll be the standard with C and O, and then sigma 2s and sigma 2s star. Finally, we can add in our electrons. So for S, both C and O have 2, but for the p orbital, C has 2 and O has 4. And so for the s orbital, both the sigma 2s and sigma 2s star are filled with 2 electrons. And then for p, pi 2p, pi 2p, and sigma 2p are all filled with 2 electrons each. And so our bond order would be 8 minus 2 over 2, and so that's equal to 3. And because all of the electrons are paired, this makes it diamagnetic. So I just wanted to close by talking about my own experiences with AP Chem. So first, general thoughts. I would recommend the course. It was challenging but rewarding, even if it was just for the knowledge that you walk away with. So for example, I just thought it was really cool to know like thermochem or molecular orbital theory. And why I decided to take it was partially due to just like the applications of it, and like for example, it's present in most of our daily objects that we use, like soap or clothes and all that. And I just thought from the beginning that it just sounded sort of interesting to learn. And I didn't really have that much knowledge of it though prior to jumping in and taking the course. In terms of what it's like, I'd say that it's sort of between bio and physics, and you sort of take both of those skills and like combine them and use them. Like for example, physics is a lot of application problems, or at least that's the case for mechanics. And bio, I feel like it's more memorization and it's more set what you need to know. And I feel like chemistry is between the two. Like there are some application problems, but it's not, I'd say, as extensive as physics is. That just might be my opinion though. And I personally didn't think it was that big of a jump from any of the other science courses that I'd taken. And nor would I say it's the hardest AP class I've ever taken. You know, hands down, that goes to AP European History, which did traumatize me sophomore year. No, I'm just kidding, sort of. So I think that the easiest part of it was probably the beginning parts, like the atomic structure and all that, and the end with like nuclear chemistry and those topics. And I think the hardest concepts were definitely the equilibrium and like thermochem and that topic. But besides the topics themselves, I think the hardest part of the course is just that the knowledge builds. And so if you don't nail concepts down like stoichiometry or equilibrium, it's harder to catch up and understand. And so in terms of advice, I'd just say, be prepared to learn and do a lot of practice problems and be organized and make sure you understand everything. And, if you found these videos helpful and you've skimmed them at least and you think that this is something that you're interested in, I'd say go for it. And best of luck. I hope you found this helpful. Thank you for listening.